Good morning, friends. We have some people not here. Christian. The three of you who are in Dr. Wolf's class, you saw the reminder about reading, right? For origins?
Just the 4 chapters.
Yeah.
Just the 4.
Noah wants to look at it on the big number option, not the small number option. Okay, before we get started, just because we have a test coming up on Tuesday, one of the things that is definitely going to be on the test that you know is going to be there is you're going to have to use a ruler to draw an accurate ray diagram for finding the image. And so if you're not clear on how to do that, it would be wise to go look at the YouTube tutorial videos, see the General College Physics tutorial videos. If you go there, there's 14, and you get down here, image construction using ray diagrams, the general one, and then for a converging lens, concave lens, it has a bunch of different that's the bottom, of different variations, so you can go over and practice how that works. Yes, that's where I started there. The link on Moodle is the link. Right, well, I can't actually point on this, but this link right here. Yes, ma'am. Let's see. Let's shut up. All right, then we can get on to the lecture, continuing on with relativity. Now remember, the test will not be covering relativity. We have the gap time, so you have time to practice, to absorb the material, and not just, we just did this yesterday and now it's on the test. So we hope to get to addition of velocities today. This is where we ended last class period with the time dilation. We worked through using Einstein's clock idea to get to an equation that said the time for the clock that was seen as moving, that's an Earth observer watching the train travel with the clock in it, was equal to a constant, well, not a constant, but a parameter gamma multiplied by the time that's measured in the rest frame of the clock. If you're inside the train car with the clock, then you have the delta t 0. And with this, gamma is defined as, so the 3 lines being defined as 1 over the square root of 1 minus v squared over c squared. When we're doing relativistic calculations, we're always going to be talking about speeds that are bigger than about 1/10 the speed of light, in which case it's really useful to define beta is equal to v over c. And so we'll talk about the speed beta, or we'll talk about the speed in terms of the speed of light. It means the same thing. And if you use that, then gamma is 1 over square root of 1 minus beta squared. So I was working with Edika on the homework this morning, and you have things where it's like, okay, so if v is equal to 0.075 c, technically, if you want to calculate gamma, you certainly can. Gamma is equal to 1 over square root of 1 minus 0.075 c. I always make my... You can do it like that, and then you see, oh, look, these c squareds cancel. Or you could just say it's equal to 1 over the square root of 1 minus 0.075 squared. I just put beta squared there. It's easier. So that's where we ended last class period. And I tried to say as we were leaving about the proper time idea. But that was not enough time to give it, fair impact. We have 2 time measurements for this clock. A person on Earth is going to measure the time per tick differently than a person in the train car with the clock. And one of our original statements about relativity is these are both valid measurements. They're both correct. But how can you have two differing measurements and say they're both correct? That's kind of like me saying the Raiders are the most awesome football team, and James saying, no, the Broncos is the Broncos you cheer for.
Vikings.
Okay. James wouldn't say that, though. That would be you. Okay, so Corso says the Vikings are the most awesome team. James says the Broncos are the most awesome team. What we're saying is it's possible for all three to be correct. With relativity, well, yes, no, in real life we know it's the Raiders. But with relativity, the different reference frames are both correct, yet different. And so that's what we're dealing with in relativity, is how we relate the measurements in the two reference frames. And so our starting point is to define the proper time. Proper does not mean correct. It means our reference time that we're going to use to relate them. So the proper time is the time measured in the rest frame of what's going on. So for our clock in the car, in the train car, the clock was at rest. So the train car is going to be the reference frame that measures the proper time for the tick of the clock, because the clock was just sitting there stationary the entire time in the car's frame. On the earth frame, the earth reference frame, the car was moving, it measures a different time. Because that parameter gamma, the Lorentz factor, is always greater than or equal to 1, then any other measurer that's not measuring the proper time is always going to measure a longer time, and thus we call it a dilated time. And so in that equation, delta t is the dilated time, it's the longer time, and delta t0 is the proper time, it's the shortest possible time that could be measured between our two events. So when you're working a problem with time dilation, it's really important to identify what's the rest frame that's going to measure the proper time. And so the rest frame is the reference frame where the clock that's doing the measuring is at rest and stationary with respect to the events. So let's just do some problem-solving strategies. Identify the two events that mark the beginning and end of what you're doing, and identify the reference frame where the clock is going to be at rest for measuring those. That tells you which reference frame measures the proper time, and then use that time dilation equation to calculate between the two reference frames. Funny units. Speed of light, I just mentioned, we'll often use beta is equal to speed over c. So if I have 0.13 c, what's beta? Yeah, it's just 0.13 without the c. Because it's, yeah. The distances, we'll often measure distances in light years. Now, this leads to some confusion to people, because light years has in it years, and a year is a unit of time. But a light year is not a unit of time. It's a unit of distance. A light year is the distance that light travels in 1 year. So 1 light year is equal to the speed of light multiplied by a year. So 1 light year is equal to c times 1 year. Then you see, speed times time is distance. It's a unit of distance. And so we can actually write the speed of light, just divide both sides by 1 year, and the speed of light is 1 light year per year, because that's what the definition of light year is. Mistakes that can be made on this. A light year is a unit for what? What type of thing are we measuring with light year? Distance, okay? What about a parsec? It's distance. Parsec stands for parallax seconds. So people like, maybe Star Wars movie makers might see the second there and think that it means time for seconds. Because it is seconds, but it's arc seconds. A parsec is a parallax arc second. It's the distance something is away to have a parallax angle of 1 arc second. And so when they talk about, made the whatever run in however many, okay, go ahead. Somebody who actually knows. What is it? The Kessel run in how many parsecs? In 12 parsecs. That's saying you made the trip from point A to point B in this distance.
It's more impressive, though.
That's why Han Solo's fantastic.
That's why he's fantastic. Now, people have apologized, made up explanations, trying to obfuscate that they didn't know what they were talking about when they made the movie by saying, well, with relativity, not only do you have time dilation, but you have what's coming up next, length contraction. And so really, if he made it in this distance and its uncontracted length is this, that's telling you how fast he was going too, right? But of course, that would be ridiculous. Okay, let's have a couple clicker questions. And by a couple, I mean 3. A sprinter runs a straight 100-meter race. Who measures the proper time for this race? And of course, this being a physics problem, we make stupid assumptions. Like the sprinter has a constant speed throughout the entire race. Constant velocity, right? They're not speeding up, they're not slowing down. Okay, we were waiting on one. There we go. Okay, 14 people said the official timekeeper stationary on Earth. 5 people said both. Christian.
Well, I put B because he is the official timekeeper. He would be the one measuring the proper time.
Interesting logic. Okay. Nobody answered the correct answer. The sprinter is the correct answer. Actually, Michael Johnson always wore a wristwatch. Now, yeah, you're right. He didn't actually, but he could have had that wristwatch, It starts when my hand accelerates forward, and yeah. We're doing a physics problem. Okay, so why is it the sprinter? What was our rule for measuring the proper time? The what? Well, stationary. With the starting and ending points the same place. So for the sprinter, the starting point's right here where I am. And my clock stays stationary with me. And the ending point is right here where I am. The starting and ending point are exactly the same place. The Earth moved under the sprinter as the sprinter's reference frame. But it was right here for the start and the finish. So the sprinter is the one that measures the proper time. If the sprinter measures the proper time, what's measured by the person on Earth? The official time, which is a dilated time. So the person on Earth is going to measure a little bit longer. Now, if you're the sprinter, that ticks you off, right? You want that shorter time. Except for how big is the difference going to be? How big is gamma when you're sprinting? It's very close to 1, exactly. And so the difference is minuscule, but it's there. So the correct answer was the sprinter. Okay, now let's go on. Question number 2. An astronaut leaves Earth in a spacecraft moving at 0.80 C and travels to a star 30 light years away. Who measures the proper time for this trip? And Christian, just so you're ready, I'm going to come back to you because it really wasn't fair when no one got it right. Okay, waiting on Brandon and Corso here. Okay. This time we had 13, 3, 1, and 2. So coming back to Christian, now, after we've gone through this once, what answer do you choose this time?
Well, using the same reasoning with the sprinter, since that question was in terms of the sprinter, this would be in terms of astronaut.
Using the same logic. For the astronaut, it's actually easier because the astronaut, you can imagine, yes, they have their chronometer, otherwise known as clock, and the person that's in the spacecraft can say, we're leaving now, punches the button. We're getting to planet X or whatever, punches the button. He's got his time. And the person in that spacecraft doesn't see anything crazy going on. He just is stationary in the spacecraft while the Earth is flying away that way and whatever his destination is flying this way. And it's easier also to recognize the validity of that reference frame. Once that spacecraft is away from Earth, you can measure its speed relative to lots of different things. You can measure it relative to the sun, relative to Jupiter, relative to another star. Say you're going to Proxima Centauri, the closest star to Earth, hence the word Proxima. About 4.3 light years away. So you're traveling toward there, you look at it and you say, wow, it's coming toward me at this speed while I'm just hanging out idling. You don't have to have your thrusters on, right? You're outside the Earth's strong gravitational field. You're just going at a constant 0 while Earth is flying away that way. Question is that? No, okay. So the person that's the astronaut sees themselves as stationary. Their clock is stationary. The starting point is right where they are, and the ending point is right where they are. So they're going to measure the proper time for the trip. Yes. Well, okay. Let's go ahead and calculate what you're talking about. So we have it's traveling at 0.80 C. Now, if you are the person on Earth, you measure the distance to be 30.0 light years away, and this spacecraft is traveling at 0.80 times the speed of light, and you can quickly calculate that the time it's going to take to make the trip on Earth, delta T Earth, is equal to that distance divided by the speed. And so we have 30 light years divided by 0.80 C. Remember, light year is a year times the speed of light. So I can cancel those C's, and I just have 30 divided by 0.8. What's 30 divided by 0.8?
37.5.
So the time it's going to take to make this trip on Earth, as measured by Earth, is 37.5 years. Now, this is the first half to answering James' question. What is going to be seen then by the astronaut for how long it takes for the trip? The astronaut is sitting in his capsule. My mind is actually doing some David Bowie lyrics here, in case you're wondering about my pause and thought, and just sees the destination coming toward him at a speed of 0.80 C. So he's just hanging out stationary, and this thing's flying toward him. He's asking how long it's going to take until it hits me. So far, we've only learned time dilation, so we can't talk about the distance he sees yet. We'll talk about the time he sees. He's going to see delta T0 is equal to delta T Earth divided by gamma. Remember, it was delta T is equal to gamma delta T0. So I just divide both sides by gamma to solve for delta T0. So what is gamma then? I have to calculate gamma. This is it. It's chosen to be easy. 0.8 squared is 0.64. 1 minus 0.64 is 0.36. Square root of 0.36 is 0.6. So that's just 1 over 0.6, which is about 1.6, roughly, between friends. Or since I have 1 over gamma here, it's going to be 37.5 years times exactly 0.6. And so what's that 37.5 years times 0.6?
22.5.
So now the person in the spacecraft, the astronaut, sees that it only takes 22 and a half years to get to there. The person on Earth says it takes 37 and a half years to get there. I said to get to there. That makes sort of sense. There's a difference there of 15 years. That seems a little problematic, doesn't it? Apparently, if you travel really fast, you don't age as quickly. That's an outcome of this time dilation. How many people here have read Orson Scott Card's most epic Ender's Game? Okay, we got 3, 4. Ender's Game is, Orson Scott Card has some physics background, and it uses, especially when you get into the second book, a lot of this time dilation idea. In the book, there was a battle between the Formics, yes, the Formics. In the second Formic War, the Formics attacked Earth, or was that the first Formic? I don't know. The second. So the Formics attacked Earth, and the people on Earth wiped them out in what turns out to be a fluke, and they immediately send their spacecraft, immediately as soon as they can get them ready, using the Formic technology, send them at near the speed of light back toward the Formic homeland so that they can attack them and wipe them out. You guys may or may not be tied into all the political things. Ender's Game, the movie, came out, and about the same time there was a big thing about marriage equality, and Orson Scott Card came out saying that he supported traditional marriage, and thus he was branded as a hater, and his book suddenly became a horrible book with talking about genocide and killing a species and how evil it is. Even though if you read the book, the whole goal is to show how evil it is to wipe out a species. Because people don't use logic and political arguments. Got to be careful. You saw that professor got fired for ranting about military people, which, by the way, I do support military people. So you have these people who are traveling near the speed of light. According to this equation, that means that the clocks in their spacecraft are traveling much more slowly than the clocks on Earth. What constitutes a clock? Well, as we saw from Einstein's original clock, that was a physical thing. Everything is going to do the same thing. So your body's metabolism is also going to be going at a different rate. So the people in those spacecraft been traveling for, 100 years? But they've only aged like 20 years because they're going really fast. And so they're still alive to go engage the Formics, and through a series of battles that are unknowingly directed by 14-year-old kids, they end up using the Maker bomb or something like that the MD device, to destroy the Formic homeworld, and hurrah, they've destroyed entire species. And then the second book is him trying to come to grips with destroying the species. But it has great ideas there of exactly how this works, time dilation. And in the later books, Ender is traveling at near speed of light for thousands of years. So he's 3,000 years after he's done all this. He's now become considered a butcher and evil person because of his own writings. That time dilation idea is just everywhere in there. So it's a great read for understanding this in a very practical sense. Coming back to James's initial question about the time, it takes less time. The people in the spacecraft have only aged 27.5 years. Well, how can you travel a distance that light takes 30 years to travel and only age 27.5 years? Would that not constitute faster than light travel? Indeed, it seems that it should be considered a violation of faster than light travel. But Einstein said, not to fear. The space-time continuum, not only can time be dilated, but the space part can be stretched as well. So we have two things that are malleable, hence the term space-time continuum, which I love to say. It's like the most nerdy thing I ever say. But the space-time continuum is a real thing. It's what we live and walk on. We think of it as a very solid three-dimensional space with no variation, and time just keeps on ticking into the future. Look up the lyrics. But what Einstein says is that's not so. You can give up a little time for space or vice versa. You can warp the space-time continuum. In fact, you have Star Trek with all of its groundbreaking scientific ideas, not groundbreaking science, but ideas. The idea of a warp drive is a real idea, one that real scientists spend real time and real money on. What is a warp drive? A warp drive, the idea is you warp the space-time continuum to take these 2 points that are far away, and you warp the space to make them right next to each other, and then you poke a hole through the space-time continuum, which sounds scary, and you hop from one place to another that's right adjacent because you warp the space-time continuum. So it's actually something that scientists have tried to figure out, are there ways that we could develop a warp drive, that we could bend the space-time continuum in a controllable fashion to make two places that would start out very far apart, close to each other, and then drill between them. So the science fiction is not purely science fiction. It's not fact at this point, but it's near there. Well, near there. I shouldn't say near there either. They're not near close to having a warp drive working, but they're working on the idea. So we could say, take this relationship and we could say, how far is the trip according to the astronaut? Let's call him Major Tom, just because that's part of what keeps going through my head here. So according to Major Tom, he sees this object coming toward him at a speed of 0.80 times the speed of light. And it's coming toward him for 22.5 years before it arrives. So he can calculate the distance in his reference frame as the distance is equal to the speed, 0.80 c, multiplied by the time, 22.5 years. 22.5 times 0.8 is says it's only 18 light years away. So he's like, well, of course I can make that 18 light year. Well, of course it can make that 18 light year trip in 22 and a half years because it's going really fast. So you have a difference in Major Tom's measurement for the time it's going to take, as well as a difference in his measurement for how long the actual trip is. And keep in mind, he's measuring the trip of the object that he's going to land on, whereas the person on Earth is measuring the trip of Major Tom. But the starting and ending points are still going to be Earth spaceship starting point, Earth, whatever the object is, ending point. Now let's go forward to the third of my clicker questions. An astronaut leaves Earth in a spacecraft moving at 0.80 C, sounds familiar, travels to a star 30 light years away, and comes back. Who measures the proper time for this trip? And you can answer now. Okay. Down to one. I should just start calling on the people who are the last ones to answer. That would be.
Well, it's a clip or not.
Oh.
It's not working.
No.
It's not working.
All right. Well, you answered two, right? The first two.
Yeah.
Okay. So we have 6, 6, 2, and 4. So we have some disagreements. It's getting harder, right? The astronaut moved out there, then moved back. The starting point and the ending point were the same place as measured on Earth and by the astronaut. Right? So it gets confusing. But if we look at this and we break it up into the two pieces, the reason I had the middle piece of the three questions, in the astronaut going out, how long did it take him to go out to that object? 22 and a half light years, or years. And assuming that he magically touches the base and changes direction and comes back at the same speed, you know that's kind of unrealistic, right? That's why in sci-fi you have inertial dampeners. Because if you have that kind of acceleration, you're squashed, as is any type of material we know of. And so the inertial dampener, the idea is to make it so inertia doesn't work, so that you can change direction with feeling no force at all. So in our magic physics problem, we have inertial dampeners. So it gets there, touches the star, and instantly is going the same speed in the opposite direction. Infinite acceleration, no problem because of the inertial dampener. How long is it going to take for the return trip? 22 and a half years again, because it's the same calculation. So it's going to take him a total of 45 years to go out and back. Now, a person on Earth measured, and they said that it took, 37 and a half years? So 37 and a half years out, 37 and a half years back, total of 75 years. 75 turns out to not equal 45. In fact, they're different by 30. And so we have going out, coming back. Which one is not, it did not say who measures the correct time. It says who measures the proper time. If I asked who measures the correct time, the correct answer would have been both. Right? Because they're both equally valid measurements. But proper doesn't mean correct. Proper is the one that's the shortest possible time for the trip. Well, we can just take those numbers and say, well, which one's shorter? I know it's kind of a ridiculous question, but yeah. The 45 is shorter than 75. So that means if one of those is the proper time, it's going to have to be the person that's the astronaut. Couple more things on this then. The astronaut goes out, comes back. They have that time. Is it proper? Well, it was proper when they were going out. When they're coming back, it's the same exact situation, so it's going to be proper for coming back. So yes, indeed, they did measure the proper time, the shortest possible time to get there and back. And the one on Earth is dilated. So if we actually were to do this, now you guys know NASA has recently done some experiments with identical twins, right? No? Well, you should. It's awesome. The identical twins are no longer identical twins. Why would they no longer be identical twins? Now, the astronaut wasn't going nearly this kind of speed, so there's really nothing going on there as far as the aging. It would be cool if we could go this speed and do that, but they didn't. But the DNA changes. They're calling, there's a 7% difference in their DNA now. Now, when I say 7% difference, you know right off the bat, they're not measuring it the same way as they measure the difference between our DNAs and chimpanzees' DNA. Because if they were measuring the same way, they would say it's an unmeasurably small difference. But it's a 7% difference in the coding, I actually didn't look at it. But how is a 7% difference in DNA? They call that his space genes. Why would you have space genes? What's going on in space that's different here? Radiation. You don't have the Earth's magnetosphere protecting you. And so you receive much higher doses of radiation, which means you have much higher mutations going on. Rates of mutations that are caused by the radiation. And a 7% difference, I don't care what your metric is, that's kind of scary. So NASA is doing identical twin experiments, but not this one, because we don't have anything that goes that fast. So this is saying we have 20-year-old astronaut Ashton, named after my grandson Ashton, who leaves Earth on a spacecraft doing the whole same thing, 0.80 C. How old is he when he returns? We've already done all the math. He's 45 years old, so he's 65. But if Ashton has a twin that's on Earth and stayed on Earth the entire time, how old would Ashton's twin be? It'd be 95. Is that possible? Well, so far, everything we've done has been theoretical. Right? Well, there's not been an ounce of, let's try it and see. That's the way Einstein worked. Everything he did was a Gedanken experiment. He thought it out, and it made sense to him. The theory said this is going to happen. But scientists aren't happy with just, oh, so you have a theory, do you? They want to see if it works. And so scientists have tested this with things like taking atomic clocks. You take two atomic clocks that keep the same time to within, 11 or 12 decimal places. Then you put one on a supersonic aircraft and have it circle the Earth for like 18 orbits, and then come back. If Einstein is wrong, if time is not malleable, the clocks will have the same time elapsed for the trip. So they do the experiment, and what do you suppose they find? They're different in agreement with relativity. Right, so that's an experiment that could have potentially disproven the hypothesis, had measurable outcome. The measurable outcome confirmed it. There are lots of other things. I don't have it with me, but in many of our phones, I'll take you this phone, we have a little GPS device. How does the GPS device work? Okay, she said it pings a satellite. We have, they call it a constellation of satellites out there orbiting the Earth. This was, of course, invented for the military so they could use this in military theaters. because of that, back when I started teaching, they intentionally fuzzed it. They used encryption, so a normal person couldn't get better than 50 meters precision for their GPS coordinates. They have taken that away now, except for in times of war, of military conflict. In military conflict theaters, they put much more sophisticated things in there so that only the U.S. and its allies can use the GPS system. So the GPS system has this constellation of satellites, and the satellites have a clock in them, an atomic clock. And essentially each satellite says, at the beep, the time will be 11:37 and 20 seconds. Ding! You guys are too young to have called time. But when I was a child, that's how we'd set the clocks. We would call time on the phone, and it would say that. And that's how you know time. That's what those satellites are doing. And so you have your little cell phone, and your cell phone is receiving the signals from the satellites. If you receive the signal from 2 satellites, then you can take the actual time here on Earth and the time that this one says and the time that this one says, and you can calculate how far you are from each one, and then you can triangulate and you know that you're on a circle. If you get a 3rd satellite, then you know how far you are from the 3rd satellite, and you can triangulate and have 2 points. One that's above the satellites and one that's below the satellites. Hot tip, we're always below the satellites. So 3 satellites is the minimum to know exactly where you are if you know that you're on the surface of the Earth. A 4th one is good because then that is going to give you one more number, and any discrepancies, you can take the average and be more sure of where you are. So that's how they work. How does that relate at all to today's lecture? Well, those satellites are orbiting the Earth. Because they're orbiting the Earth, they're traveling at a reasonable rate of speed, which means their clocks aren't going to keep the right time. It turns out there is another type of relativity, the general relativity, that says that mass warps the space-time continuum. That is, that time travels at a different rate when you're close to a massive object than when you're not. And so they actually have to calibrate those clocks. So on Earth, they do not keep correct time. But when they're in orbit farther from the Earth's mass and traveling at a different speed, they will keep the right time. And so that's a very practical example that is taking the relativity, both the general relativity and the special relativity, into account so that you can have clocks keeping correct time while they're orbiting the Earth. Back to this. This problem with the 2 twins, one 95, one 65, 45 plus 20, 65, I think I said 75 right, I don't know. 165, 195. This is called the twin paradox because you have the 2 twins saying, well, everything we've done, we don't have a paradox. But if you take the person on Earth, the person on Earth says, I'm not traveling, hence I should be measuring the proper time for my measurements. The person in the spacecraft says, I'm not traveling, I should be measuring the proper time for my measurements. And so it comes down to, well, who's really measuring the proper time? How can this be? They're both stationary. Any answers? It's what? Well, all of relativity is the difference in reference frame, so it definitely has to do with that. There is a special relativity caveat that I have not brought up today that's vital, that helps us differentiate these. What are our starting points for special relativity, or one starting point really for special? Has to be in a special reference frame. An inertial reference frame. So special relativity only applies for inertial reference frame. The person on Earth is in inertial reference frame. They can use special relativity calculations throughout the entire trip. The person in the spacecraft can't because they're going to accelerate when they turn around and come back. There's no 2 ways around it. So in a realistic scenario, During the accelerations, you're going to have some different observations. During the acceleration, the person on Earth simply says, well, that clock is stationary in their reference frame. Their reference frame is speeding up, and so the clock is slowing and slowing and slowing. The person on Earth is making that measurement, their inertial reference frame. That's the one that we can use our calculations on. The person that's in the spacecraft, when they're taking off and speeding up, they're accelerating, and what they're going to see is, wow, my twin on Earth is aging really fast while I'm speeding up, or while the Earth is accelerating away from me, is what they would say. And then when they're at constant speed, then their twin on Earth is aging really slowly. Then when they accelerate to turn around and come back, their twin on Earth ages really fast again. And then slowly when it's at constant speed, and then ages really fast when they stop. And so they have these periods where their twin on Earth was aging really fast compared to them. And when you put it all together, the twin on Earth ages the extra 30 years. So you really are going to have age differences. So if you're an airline pilot, you might add a second to your lifetime by all that time spent in space. Except pilots receive a lot more radiation because they have less protection with the atmosphere, and so they might be causing things to lower their lifespan, like more susceptibility to cancer. In other words, don't say, oh, I'm going to become a pilot so I can live an extra second. Okay, length contraction. Coming back to, I talked about, oh my goodness, we are not going to get to velocity addition, but we're going to get to length contraction. I talked about the person in the spacecraft actually sees the distance that the object coming toward him has to travel is shorter than the distance measured on Earth, the length contraction. Now, length contraction, an important thing about length contraction is it's only in the direction parallel to motion. And the equation for length contraction, which just comes from taking our time dilation equation and putting it into distance equals velocity times time like we did, is that the length measured in one reference frame is equal to the length measured in the other reference frame divided by gamma, where the other reference frame in my equation is the proper length. Once again, it's not the correct length, it's the proper length. It is the length measured in the proper reference frame for length. Proper reference frame for length is not the same as the proper reference frame for time. So don't say, oh, that measures the proper time, it must also measure the proper length. Not so. The proper length is the length measured in the reference frame where the distance traveled is, or the starting and end points are stationary. So if I am driving from here to Omaha, I'm in my car, and of course we're supposing, this being physics class, that I am driving at constant velocity the entire time. I'm measuring the proper time for the trip because my clock will be at the starting point here in Lincoln, the ending point in Omaha, and the clock stayed stationary. But somebody on Earth would measure the proper distance, the proper length for that trip, because the starting point and ending points are fixed on Earth and stationary. So you have a different reference frame for the proper length as you do for the proper time. In the astronaut's trip, the astronaut sees Earth is moving, and the star he's going to is moving. So he's not measuring the proper length for the trip. The person on Earth sees their position and that star is stationary. That's going to be the proper length. Notice we have length contraction. We had time dilation. The time in something other than the proper frame is always longer. The length in some other reference frame is always going to be shorter. And so Major Tom measured a shorter distance for the trip because it was a moving object that he was measuring the length of. So we have time dilation and length contraction. And remember, it's super important. It's only lengths that are parallel to the velocity that are contracted. Perpendicular lengths do not change. So if I am traveling toward you and I have this meter stick, you'll see the height of the meter stick is exactly the same, but the width will be smaller. So my key is if I'm running toward you, you'll see me as skinnier because of length contraction, but my height will stay the same. That's bueno. Now, if I'm going like this, head first towards you, It's the opposite of bueno. It's no bueno. Because then you're going to see me shortened, but staying with the same girth. That's not the way I want to be seen by my friends. Okay, we're out of time. We will talk about velocity addition next week.